In 1964, a physicist named John Stuart Bell published a theorem that would shatter our most fundamental assumptions about the nature of reality itself, proving mathematically that the universe cannot be both local and real in the way we intuitively understand those concepts. This discovery, later confirmed by decades of painstaking experiments, reveals that either objects don't have definite properties until measured, or information can somehow influence distant events instantaneously, violating what Einstein called the ultimate speed limit of causality. The implications are so profound and unsettling that they force us to question whether objective reality exists at all when nobody's looking, whether the moon is really there when we're not observing it, and what role consciousness might play in the unfolding of physical events across the cosmos. If you're captivated by these reality-bending mysteries that challenge everything we think we know about existence, make sure to subscribe and leave a thumbs up to help me continue exploring the deepest puzzles at the heart of quantum mechanics and consciousness. Before we continue, let me know in the comments where you're watching from. One quick question for you. If you could know the answer to one fundamental question about quantum mechanics, would you want to understand the measurement problem, the nature of quantum entanglement, or the role of consciousness in collapsing wave functions? Let me know in the comments and I'll pick the most thought-provoking response. The consequences of Bell's theorem and the experimental violations of Bell's inequalities are absolutely staggering in their implications for our understanding of reality. Quantum entanglement, the phenomenon that Einstein famously derided as spooky action at a distance, has been confirmed beyond any reasonable doubt through thousands of experiments conducted in laboratories around the world. When two particles become entangled through interaction, measuring the quantum state of one particle instantaneously determines the state of the other, regardless of the distance separating them, whether that's a few meters in a laboratory or potentially billions of light years across cosmic space. This isn't just correlation between pre-existing properties like two gloves in separate boxes, where examining one tells you about the other. Bell's theorem proves mathematically that the correlations observed in quantum mechanics are stronger than any correlation that could arise from particles carrying predetermined properties, demonstrating that quantum particles genuinely don't possess definite properties until the moment of measurement. But here's what makes this discovery truly mind-bending and paradoxical in ways that challenge our deepest intuitions about causality and the structure of spacetime. The experimental violations of Bell's inequalities seem to suggest that information can travel faster than light, allowing one measurement to instantly affect another measurement performed simultaneously in a distant location. Yet quantum mechanics also prohibits using entanglement to send signals or transmit information faster than light, creating an apparent contradiction that has puzzled physicists and philosophers for decades. This tension between non-locality and the prohibition on superluminal signaling represents one of the deepest conceptual puzzles in quantum mechanics, forcing us to reconsider what we mean by causality, locality, and the flow of information through space-time. The story of quantum mechanics and its paradoxes illustrates how science progresses not through accumulation of certain knowledge, but through discovery of ever deeper mysteries that force us to question our most basic assumptions about reality. Each answer generates new questions, each resolved paradox reveals new puzzles, and each successful prediction uncovers new phenomena that don't fit our existing frameworks. The development of quantum mechanics in the early 20th century didn't solve the problems of atomic physics so much as reveal that reality operates according to principles utterly foreign to everyday experience and classical intuition. Similarly, Bell's theorem and the experimental confirmation of quantum entanglement didn't settle debates about quantum foundations, but instead opened new questions about locality, realism, causality, and the role of observation in determining physical reality. The measurement problem that troubled the founders of quantum mechanics continues to generate competing interpretations and philosophical debates, despite nearly a century of theoretical and experimental work, suggesting that understanding quantum mechanics might require conceptual revolutions as profound as those that gave birth to the theory itself. The quest to understand quantum reality connects to humanity's oldest philosophical questions about the nature of existence, knowledge, and the relationship between mind and matter. Ancient debates between Plato and Aristotle about whether universals exist independently or only in particular instances find echoes in contemporary arguments about whether the wave function represents real physical entities or merely human knowledge. Buddhist concepts of dependent origination and emptiness, where things exist only in relation to other things without independent essence, resonate with quantum mechanics' emphasis on relational properties and contextuality. The observer effect in quantum mechanics has been compared to idealist philosophies that view consciousness as primary and matter as derivative, though most physicists resist such interpretations as reading too much philosophy into straightforward physical phenomena. These connections suggest that quantum mechanics might be revealing aspects of reality that ancient philosophers intuited but couldn't formulate precisely without modern mathematics and experimental methods, or alternatively that we're projecting conceptual frameworks onto nature that reflect our cognitive limitations rather than objective features of reality itself. The unification of quantum mechanics with general relativity remains the greatest unsolved problem in theoretical physics, with numerous approaches competing to create a consistent theory of quantum gravity. String theory proposes that fundamental constituents are one-dimensional extended objects whose vibrational modes correspond to different particles, requiring extra spatial dimensions and mathematical structures of extraordinary complexity to achieve consistency. The theory has achieved remarkable successes, including deriving black hole entropy, providing concrete realizations of holographic principles through ADS, CFT correspondence, and unifying all forces, including gravity, within a single mathematical framework, but it faces criticisms for making no testable predictions at currently accessible energies and for the vast landscape of possible vacuum states that seems to sacrifice predictive power for flexibility. Loop quantum gravity takes a different approach, directly quantizing the geometry of spacetime itself through discrete loops and networks that create granular structure at the Planck scale, successfully addressing singularities in black holes and cosmology, and making potentially testable predictions about dispersion of light from distant gamma-ray bursts, but struggling to recover general relativity smoothly in the classical limit and to incorporate matter and forces beyond gravity. Alternative approaches, including causal set theory, asymptotic safety, emergent gravity, and various attempts to understand spacetime as emergent from more fundamental quantum information structures, continue to develop, with researchers hoping that upcoming gravitational wave observations, quantum gravity effects in the cosmic microwave background, or unexpected discoveries from quantum computers or particle colliders might provide empirical guidance for choosing among these competing frameworks. The anthropic principle and multiverse concepts connect quantum mechanics to questions about why our universe has the properties that permit life and consciousness to exist. The observed values of fundamental constants like the cosmological constant, the fine structure constant determining electromagnetic interaction strength, and the mass ratios between different particles all seem remarkably fine-tuned for life, with small changes in any direction producing universes where stars couldn't form, chemistry would be impossible, or conditions would be hostile to complexity. The strong anthropic principle suggests this fine-tuning requires explanation through design or purpose, while the weak anthropic principle simply notes that observers can only exist in universes compatible with their existence, making the apparent fine-tuning unsurprising as a selection effect. The multiverse interpretation of quantum mechanics in Everett's many worlds picture, combined with eternal inflation models, or the string theory landscape, naturally produces vast numbers of universes with different physical constants, making anthropic selection inevitable and removing the need for design or purpose to explain fine-tuning. Critics argue that multiverse explanations abandon the scientific goal of understanding why nature has specific properties, replacing explanation with anthropic selection that seems untestable and potentially unscientific, while supporters contend that if multiverse structures follow from our best physical theories, we must accept their implications for how we understand apparently fine-tuned constants, even if this understanding differs from traditional scientific explanation. The relationship between quantum mechanics and free will represents another area where physics intersects with philosophy and human self-understanding. If quantum measurements have truly random outcomes not determined by any hidden variables or prior causes, as suggested by violations of Bell's inequalities and the apparent indeterminism of quantum mechanics, does this indeterminism provide room for free will by showing that physical events aren't completely determined by prior states? Or does randomness fail to provide meaningful freedom, since random events are just as incompatible with free will as deterministic events, with neither capturing the sense of agency and control we associate with free choice? Compatibilist positions argue that free will doesn't require indeterminism, but rather appropriate kinds of causal connections between beliefs, desires, and actions, making quantum indeterminism irrelevant to questions of freedom and responsibility. Libertarian free will theories that require indeterminism face the challenge of explaining how quantum randomness in neurons could underwrite meaningful agency rather than just introducing noise into neural processing. Some philosophers and neuroscientists have proposed quantum consciousness theories where subjective experience involves collapse of quantum superpositions through conscious choice, potentially providing a physical mechanism for free will, but these ideas remain highly speculative and lack clear experimental support or theoretical development. The interpretation of probability in quantum mechanics raises deep questions about the nature of randomness, determinism, and physical law. The Born rule that derives probabilities from wave function amplitudes is one of quantum mechanics' most basic principles, yet its origin and justification remain somewhat mysterious and contentious. In many worlds interpretations, deriving the Born rule presents particular challenges since all possible outcomes occur with certainty across different branches, raising questions about why we should assign probabilities at all and why those probabilities should follow the Born rule rather than simply counting branches equally. Various derivations have been proposed based on decision theory, symmetry arguments, and self-locating uncertainty, but debates continue about whether these derivations succeed or beg the question by assuming what they aim to prove. In Copenhagen interpretations, the Born rule is typically taken as a fundamental postulate, connecting abstract wave functions to observable frequencies, but this leaves unexplained why nature should follow this particular rule rather than alternative probability assignments. Pilot wave theories and spontaneous collapse models provide different stories about probability, with pilot wave theories deriving probabilities from assumptions about initial conditions and equilibrium distributions, while collapse theories derive them from stochastic dynamics of collapse processes, illustrating how probability concepts depend intimately on underlying interpretational commitments about quantum reality. The experimental verification of quantum mechanics continues to probe edge cases and unusual regimes where classical intuitions fail most dramatically. Tests of quantum mechanics with antimatter have confirmed that antiparticles follow identical quantum rules to particles, with antimatter interferometry experiments demonstrating quantum superposition and entanglement for positrons and antiprotons. Gravitational effects on quantum systems are being tested through atom interferometry in different gravitational potentials, with experiments confirming that quantum clocks in superpositions of different heights experience different proper times according to general relativity, successfully combining quantum and gravitational effects in ways that challenge both theories. Proposed experiments would test quantum entanglement across black hole event horizons, though practical implementation faces obvious challenges, and theoretical analyses explore whether Hawking radiation from black holes could be entangled with the black hole interior or previously emitted radiation in ways that preserve quantum information. Quantum mechanics in curved spacetime remains a frontier where neither quantum field theory nor general relativity has been fully tested experimentally, with most work proceeding through theoretical calculations that await future observations of quantum effects in strong gravitational fields from neutron star mergers, black hole accretion, or cosmological evolution. The role of symmetry in quantum mechanics connects abstract mathematical structures to physical conservation laws and fundamental principles. Noether's theorem relating continuous symmetries to conservation laws applies in quantum mechanics through unitary representations of symmetry groups acting on Hilbert spaces, with time translation symmetry corresponding to energy conservation, spatial translation to momentum conservation, and rotational symmetry to angular momentum conservation. Gauge symmetries play crucial roles in quantum field theories describing fundamental forces, with the electromagnetic, weak, and strong forces all arising from requiring invariance under local gauge transformations of quantum fields. The deeper significance of gauge symmetries remains somewhat mysterious, with debates about whether they represent real physical redundancies in our descriptions or fundamental features of nature that constrain possible physical laws. Spontaneous symmetry breaking, where the laws of physics possess symmetries not shared by particular solutions or ground states, explains phenomena from ferromagnetism to the masses of elementary particles through the Higgs mechanism. These connections between symmetry and physics suggest that quantum mechanics might be exploring a space of possible theories constrained by consistency requirements and mathematical structures, with the particular quantum theory describing our world selected by symmetry principles we haven't fully understood. The implications of quantum mechanics for our understanding of identity and individuality challenge classical intuitions about what makes objects the same or different over time. Quantum statistics distinguishing bosons from fermions through symmetric or antisymmetric wave functions under particle exchange suggest that identical quantum particles might not have individual identities at all, with the quantum state describing collections of indistinguishable particles rather than tracking specific individuals. This quantum indistinguishability seems to violate Leibniz's principle of the identity of indiscernibles, which holds that objects sharing all properties must be identical, since quantum particles can share all intrinsic properties yet remain numerically distinct in the sense that two particles exist rather than one. Debates about whether quantum particles are individuals focus on whether we should adopt Hayekism, the view that individual identity transcends qualitative properties, or anti-Hayekism, the view that identity reduces to shared or differing properties. These abstract metaphysical questions connect to physical phenomena like quantum statistics and the Pauli exclusion principle that prevents multiple fermions from occupying the same quantum state, suggesting that the metaphysics of identity has empirical consequences through its effects on allowed quantum states and observable behavior. The development of quantum technologies over coming decades promises to transform society in ways comparable to the classical information revolution of the 20th century. Quantum computers, achieving fault tolerance and scaling to millions of qubits, could solve problems in drug discovery, materials design, optimization, and cryptography that are completely intractable for classical computers, regardless of technological advances. Quantum simulation of complex molecules and materials would allow predictive design of new catalysts, pharmaceuticals, and superconductors by accurately modeling quantum many-body systems that defeat classical simulation methods. Quantum cryptography and communication could provide provably secure information transfer immune to any computational attack, protecting sensitive data against future quantum computers that would break current encryption schemes. Quantum sensors and metrology approaching fundamental quantum limits could enable new medical diagnostics, underground resource mapping, dark matter detection, and tests of fundamental physics that are impossible with classical technology. These quantum technologies would represent not merely incremental improvements over existing capabilities, but qualitatively new applications, exploiting quantum coherence, entanglement, and interference in ways that have no classical analogues. The societal and philosophical implications of quantum technologies extend beyond practical applications to transform how we understand information, privacy, and the boundaries of physical possibility. Quantum computers capable of breaking current cryptographic systems would require completely new approaches to cybersecurity and digital privacy, potentially disrupting financial systems, government communications, and internet security if classical encryption is defeated before quantum-resistant alternatives are deployed. The ability to create and manipulate complex entangled states might enable new forms of distributed quantum computation and communication that challenge our concepts of information, locality, and the boundaries between separate systems. Quantum sensing of previously undetectable signals could raise privacy concerns if it enables surveillance capabilities that penetrate current physical barriers, while simultaneously offering medical and scientific benefits through unprecedented measurement precision. The development of quantum technologies would also test the limits of human understanding and control over quantum systems, as we attempt to engineer coherent quantum states of ever-increasing complexity while battling decoherence and developing intuitions for quantum behavior that remains deeply counterintuitive even to experts. The story of quantum mechanics from its origins in early 20th century atomic physics to contemporary experiments probing entanglement, superposition, and the measurement problem represents one of humanity's greatest intellectual achievements and deepest ongoing mysteries. The theory has survived every experimental test over nearly a century, making predictions confirmed to extraordinary precision across domains from particle physics to cosmology. Yet the theory's interpretation and the nature of the reality it describes remain controversial and puzzling, with competing frameworks offering radically different ontologies and epistemologies while making identical empirical predictions. This situation seems almost unique in physics, where theories typically converge on specific interpretations as evidence accumulates and understanding deepens. The persistence of the quantum measurement problem and the proliferation of interpretations might indicate that we're missing some crucial insight that would make quantum mechanics obviously correct and intuitive, or, alternatively, that nature genuinely is as strange as quantum mechanics suggests, and that multiple mathematical formulations capture different aspects of this quantum reality without any being uniquely correct. The future resolution of quantum foundations might come from unexpected directions, perhaps through discoveries in quantum gravity, quantum cosmology, or quantum information theory that weren't anticipated by the theory's founders. The connections between entanglement and spacetime geometry, suggested by ER equals EPR and holographic principles, hint that quantum mechanics and gravity are more deeply related than previously imagined, with geometry emerging from entanglement patterns rather than being fundamental. The role of information and complexity in quantum mechanics, explored through quantum information theory and computational complexity, suggests that understanding quantum mechanics might require thinking about physical systems primarily in terms of information processing and correlations, rather than traditional concepts of particles and fields. The measurement problem might be resolved through better understanding of decoherence, quantum Darwinism, and the emergence of classicality, recognizing that the quantum classical boundary isn't a fundamental cut in nature, but an emergent distinction arising from information-theoretic considerations about which observables decohere rapidly in typical environments. Whatever future discoveries reveal about quantum reality, the theory has permanently transformed human understanding of nature, causality, and the limits of knowledge. The recognition that systems can exist in superpositions of multiple states, that measurements create rather than merely reveal properties, that distant events can be correlated in ways that violate local hidden variable theories, and that reality at its deepest levels seems to resist. Description in classical terms represents a conceptual revolution as profound as any in human intellectual history. The implications extend beyond physics to influence philosophy, computer science, information theory, and our basic understanding of what it means for something to exist or to be real. The continuing quest to understand quantum mechanics, to test its predictions in new regimes, to develop new interpretations that might resolve long-standing puzzles, and to exploit quantum phenomena for practical technologies remains one of the great adventures of human thought. Whether quantum mechanics represents our final theory of microscopic reality, or will eventually be superseded by even stranger theories we cannot yet imagine, the journey of discovery has revealed that the universe is far more mysterious, subtle, and wonderful than our ancestors could have dreamed, challenging us to expand our concepts of reality, knowledge, and existence itself to accommodate the quantum nature of the physical world. The relationship between quantum mechanics and thermodynamics opens yet another window into the foundations of physics, connecting microscopic quantum behavior to macroscopic phenomena like temperature, entropy, and the arrow of time. The second law of thermodynamics, stating that entropy always increases, seems to conflict with the reversible unitary evolution of quantum mechanics, creating a puzzle about how irreversible thermodynamic behavior emerges from reversible quantum laws. The resolution involves recognizing that thermodynamic entropy reflects our ignorance about microscopic quantum states, with macroscopic systems having enormous numbers of possible microstates corresponding to each macrostate characterized by temperature and pressure. When we measure only coarse-grained thermodynamic variables, we lose information about quantum phases and coherences, with this information loss appearing as entropy increase, even though the full quantum state evolves reversibly. This connection between information and entropy, formalized through von Neumann entropy and quantum information theory, suggests that the second law of thermodynamics is fundamentally about information flow rather than physical degradation, with apparent irreversibility arising from practical limitations on accessing and controlling microscopic quantum details rather than from fundamental time asymmetry in physical laws. The quantum Zeno effect and its inverse, the anti-Zeno effect, demonstrate how measurement can dramatically alter quantum evolution in counterintuitive ways. The quantum Zeno effect shows that frequent measurements of whether a system remains in its initial state can actually prevent quantum transitions that would otherwise occur, effectively freezing quantum evolution through repeated observation. This phenomenon takes its name from Zeno's paradox about the impossibility of motion, with quantum measurements playing the role of Zeno's infinitely many observations that seem to prevent change. The anti-Zeno effect shows the opposite behavior, where measurements can actually accelerate quantum transitions under certain conditions, with the direction of the effect depending on the system's energy spectrum and the relationship between measurement intervals and natural evolution timescales. These effects have been demonstrated experimentally with atoms, ions, and other quantum systems, confirming that the act of measurement can dramatically influence quantum dynamics in ways that depend sensitively on measurement timing and strength. The practical applications include quantum error correction, where measurements are used to prevent unwanted quantum transitions, and quantum control, where carefully timed measurements steer systems toward desired states, illustrating how measurement is not merely a passive observation, but an active intervention that shapes quantum reality. The role of contextuality in quantum mechanics represents a subtle but profound departure from classical physics that goes beyond complementarity and uncertainty relations. The Cauchy-Specker theorem, proved in 1967, demonstrates that quantum observables cannot consistently be assigned definite values independent of measurement context, even in hidden variable theories that abandon locality. The theorem shows that attempting to assign predetermined values to all quantum observables leads to logical contradictions, proving that measurement context necessarily affects outcomes in ways that cannot be explained by revealing pre-existing properties. This contextuality means that the value obtained when measuring an observable depends not just on the system's state and the measured property, but also on which other observables are measured simultaneously, creating a holistic interconnection between measurements that has no classical analog. Experimental tests using quantum systems with multiple observables have confirmed contextuality violations that rule out non-contextual hidden variable theories, providing another nail in the coffin for classical realism alongside Bell's theorem. The discovery of quantum contextuality has inspired new approaches to quantum computation and quantum games, where quantum strategies can outperform any classical strategy by exploiting contextual correlations that classical systems cannot reproduce. The emergence of space-time from quantum entanglement represents one of the most revolutionary ideas in contemporary theoretical physics, suggesting that space and time might not be fundamental, but rather emergent phenomena arising from patterns of quantum information. The ER equals EPR conjecture proposed by Juan Maldacena and Leonard Susskind suggests that quantum entanglement between particles and wormhole connections between regions of spacetime might be two descriptions of the same underlying phenomenon, unifying quantum mechanics and gravity through information theoretic principles. In the ADS CFT correspondence, the geometry of spacetime in the bulk emerges from entanglement patterns in the boundary quantum field theory, with distances in the bulk corresponding to strengths of quantum correlations in the boundary, providing concrete examples where spacetime is demonstrably emergent from quantum information. The Ryu-Takayanagi formula relating entanglement entropy to geometric areas of minimal surfaces in spacetime provides a precise mathematical connection between quantum information and spacetime geometry, suggesting that Einstein's equations might be rewritten as statements about how quantum entanglement organizes itself across space. These ideas suggest that asking what happens to space and time at the Planck scale might be the wrong question, since space and time might not exist as fundamental entities at that scale, but only emerge at larger scales from more primitive quantum degrees of freedom whose nature we don't yet understand. The black hole complementarity principle proposed by Leonard Susskind represents an attempt to resolve information paradoxes by suggesting that different observers can have complementary but apparently inconsistent descriptions of the same physical situation. An observer falling into a black hole experiences nothing special at the horizon and sees information falling smoothly into the interior, while a distant observer sees the same information thermalize at the horizon and eventually re-emerge in Hawking radiation, with neither description being more correct than the other, and no observer able to verify both simultaneously. This radical idea challenges the assumption of observer-independent reality that most physicists take for granted, suggesting that quantum gravity might require abandoning the notion that there's a single objective description of events that all observers would agree on. Critics argue that complementarity seems to allow contradictory descriptions that should lead to paradoxes if observers compare notes, while supporters contend that the extreme conditions near black hole horizons make such comparisons impossible in practice, preserving logical consistency while allowing multiple complementary descriptions. The debate illustrates how quantum gravity might require conceptual revolutions even more radical than those quantum mechanics already demanded, potentially forcing us to abandon not just classical determinism and locality, but even the assumption that physical reality has a single objective description independent of observers. The problem of quantum measurement in cosmology takes on unique challenges when we consider that our universe might be the only one, or when we try to apply quantum mechanics to the universe as a whole. If the universe is truly unique, with no external environment or observers, the Copenhagen interpretation's reliance on measurement by external classical systems seems inapplicable, since there's no outside to measure from and nothing classical that isn't already part of the quantum system. The many worlds interpretation naturally applies to cosmology, since it requires no external measurement or collapse, with the universe splitting into branches for every quantum event, including the early universe's quantum fluctuations. But this raises puzzles about probability and how to make predictions when all outcomes occur. The consistent histories approach, developed by Griffiths, Gell-Mann and Hartle, attempts to assign probabilities to different cosmic histories without requiring measurement or observers, selecting consistent sets of histories through decoherence conditions that eliminate quantum interference between different possibilities. These frameworks struggle with conceptual issues about how to assign probabilities or select preferred histories without circular reasoning or unmotivated assumptions, illustrating that applying quantum mechanics to cosmology exposes interpretational problems that can be avoided or ignored when studying laboratory systems with external observers and well-defined measurement apparatuses. The question of whether quantum mechanics applies to consciousness itself remains one of the most speculative and controversial areas, connecting physics to philosophy and cognitive science. While most neuroscientists argue that brains are warm, wet, noisy environments where quantum coherence would be destroyed far too quickly to play functional roles in cognition, some researchers continue exploring whether quantum effects might be relevant to certain aspects of consciousness or brain function. Stuart Hameroff and Roger Penrose's orchestrated objective reduction theory proposes that consciousness arises from quantum computations in microtubules within neurons, with quantum superpositions collapsing through gravitational effects when they reach certain thresholds, potentially explaining the unity and binding of conscious experience. Critics point out that microtubules exist at temperatures and in environments where decoherence times would be far too short for meaningful quantum computation, and that there's no clear evidence for quantum effects in neural processing or for consciousness requiring quantum mechanics rather than classical computation. More recently, researchers have found some suggestive evidence for quantum effects in bird navigation, photosynthesis, and possibly olfaction, suggesting that biology might employ quantum mechanics more widely than previously thought, though these systems use clever evolutionary tricks to protect quantum coherence rather than operating at the temperatures and scales of human brains. The question of whether consciousness could itself be a quantum phenomenon or requires quantum mechanics for explanation remains open despite decades of speculation, with most physicists and neuroscientists remaining skeptical while acknowledging our profound ignorance about the physical basis of subjective experience. The role of symmetry breaking in quantum field theory provides crucial insights into how simple laws can generate complex phenomena and why our universe has the specific properties we observe. The Higgs mechanism explains how gauge bosons acquire mass through spontaneous symmetry breaking, with the Higgs field settling into a non-zero vacuum expectation value that breaks the electroweak symmetry and gives masses to W and Z bosons while leaving photons massless. This symmetry breaking is crucial for explaining why the electromagnetic and weak forces have such different strengths and ranges, despite being unified at high energies into a single electroweak interaction. The discovery of the Higgs boson at the Large Hadron Collider in 2012 confirmed this mechanism and represented a triumph for quantum field theory's ability to predict new particles and phenomena from theoretical consistency, requirements, and symmetry principles. Phase transitions in the early universe, involving symmetry breaking, might explain the abundance of matter over antimatter. Through baryogenesis mechanisms, the formation of cosmic strings, or other topological defects that could have seeded structure formation, and potentially the origin of inflation itself, if driven by symmetry breaking in unknown high-energy field theories. These connections between symmetry, quantum field theory, and cosmology suggest that understanding quantum mechanics at its deepest levels requires grappling with how symmetries constrain physical laws and how symmetry breaking generates the rich structure and complexity we observe in bees with nature. The concept of quantum discord and other non-classical correlations beyond entanglement has revealed that entanglement is not the only quantum feature distinguishing quantum from classical systems. Quantum discord measures how much a quantum state's correlations are disturbed by local measurements, with non-zero discord indicating genuinely quantum correlations, even in some separable states that aren't entangled. This discovery shows that the quantum classical boundary is more subtle than early researchers realized, with quantum weirdness appearing in correlations and information theoretic properties beyond just entanglement. Some quantum computational speedups and quantum communication advantages can be achieved using states with quantum discord, but no entanglement, suggesting that non-classical correlations more general than entanglement might be responsible for quantum advantages in information processing. The study of quantum discord has led to deeper understanding of which quantum features are truly responsible for computational advantages, with ongoing debates about whether entanglement is necessary for quantum speedup or whether discord and other measures of quantumness might be more fundamental for understanding quantum information processing advantages. The interface between quantum mechanics and special relativity in quantum field theory successfully reconciles quantum mechanics with relativity, but introduces new conceptual puzzles about particle creation, the vacuum state, and the nature of fields. Quantum field theory treats particles as excitations of quantum fields pervading spacetime, with creation and annihilation operators adding or removing quanta of energy from field modes in ways that have no non-relativistic analog. The concept of particles becomes observer-dependent in quantum field theory, with different accelerated observers disagreeing about the number and properties of particles present due to the Unruh effect, where accelerated observers see thermal radiation, where inertial observers see vacuum. This observer dependence of particle number challenges naive interpretations of particles as objective entities, suggesting that only fields or field operators have observer-independent meaning, while particle descriptions are convenient approximations valid in special coordinate systems or for approximately inertial observers. The vacuum state in quantum field theory is incredibly rich, filled with virtual particles and quantum fluctuations that have measurable effects through vacuum polarization, the Casimir effect, and contributions to particle masses and interaction strengths, demonstrating that even empty space has complex quantum structure in field theory that goes far beyond the simple ground state of quantum mechanical systems. The pursuit of experimental signatures of quantum gravity represents one of the greatest challenges in contemporary physics, requiring either incredibly high energies near the Planck scale or else incredibly sensitive measurements of tiny effects that might accumulate over cosmic distances or long times. Proposed signatures include modifications to special relativity at very high energies that might show up as energy-dependent speed of light for photons from distant gamma-ray bursts, quantum gravitational fluctuations that might be detectable through their effects on gravitational wave signals from black hole mergers, or violations of quantum mechanics like spontaneous collapse that might be triggered by gravitational interactions and could be tested with increasingly massive quantum superpositions. Space-based detectors for cosmic rays, gamma rays, and gravitational waves might have the sensitivity to detect these subtle signatures if they exist at levels predicted by some quantum gravity theories, though most predictions suggest effects far too small for any foreseeable technology. Alternative approaches to testing quantum gravity include searching for deviations from quantum mechanics in laboratory experiments, testing the quantum properties of gravitational interactions through gravitational quantum effects on quantum systems, or looking for cosmological signatures of quantum gravity in the cosmic microwave background from the very early universe when quantum gravitational effects might have been significant. The challenge is that quantum gravity effects are suppressed by the Planck mass, an energy scale about 10–16 times higher than energies achievable at the Large Hadron Collider, making direct tests of quantum gravity extraordinarily difficult with current or near-future technology. The philosophical question of scientific realism versus instrumentalism takes on particular urgency in quantum mechanics, where the theory's empirical success is unmatched, but its interpretation remains deeply controversial. Scientific realists argue that successful theories approximately describe reality and that quantum mechanics must be telling us something true about the world, even if we don't yet fully understand what, while instrumentalists contend that theories are merely tools for organizing experiences and making predictions without necessarily describing observer-independent reality. The quantum measurement problem provides a key battleground for these debates, with realists insisting there must be some objective fact about what happens during measurement even if we don't know what it is, while instrumentalists are comfortable viewing measurement outcomes as primitive experiences that don't require deeper explanation in terms of underlying reality. Entity realists argue we should believe in entities like electrons and photons because we can manipulate them experimentally and use them to investigate other phenomena, even if we remain agnostic about whether theories describing their properties are literally true. Structural realists propose that what we should believe in is the mathematical structure of theories rather than specific ontological pictures, with quantum mechanics revealing relational structures and symmetries that remain stable across theory change, even if our interpretations of what the mathematics describes continue to evolve. The future of quantum mechanics over the next century might see revolutionary discoveries that make our current debates seem quaint, much as 19th century debates about the luminiferous ether or the reality of atoms were resolved by 20th century developments. Quantum computers, achieving millions of qubits and fault-tolerant operation, might probe quantum mechanics in regimes of unprecedented complexity, potentially discovering deviations from quantum mechanics that point toward new physics, or confirming that quantum principles apply without modification to arbitrarily large systems. Space-based quantum experiments testing entanglement across solar system distances, quantum effects in gravitational fields from the Sun and Earth, and searches for quantum gravity signatures in cosmic rays and gravitational waves might reveal new physics at the intersection of quantum mechanics and gravity. Laboratory experiments creating quantum superpositions of increasingly massive objects approaching microgram or even milligram scales might discover spontaneous collapse mechanisms or other modifications to quantum mechanics that become relevant at large masses, resolving the measurement problem empirically rather than philosophically. Advances in quantum biology might reveal that living systems exploit quantum mechanics more broadly than currently recognized, potentially even in neural processing or consciousness, though most experts expect classical physics to suffice for understanding life, even if some specific mechanisms employ quantum effects. Whatever discoveries await, quantum mechanics has proven itself one of the most successful and profound theories in human history, forever changing how we understand reality, causality, information, and the deep structure of physical law underlying the quantum fabric of our universe. Of quantum entanglement. And Bell's theorem begins in the early decades of the 20th century, when physicists were grappling with the bizarre implications of quantum mechanics, a revolutionary framework that described the behavior of atoms and subatomic particles in ways that seemed to violate common sense and challenge classical intuitions. In 1935, Albert Einstein, working with Boris Podolsky and Nathan Rosen, published a paper that became known as the EPR paradox, arguing that quantum mechanics must be incomplete because it predicted correlations between distant particles that seemed to require either faster-than-light influence or the existence of hidden variables that predetermined measurement. Outcomes. Einstein believed deeply in what philosophers call local realism, the idea that physical systems possess definite properties independent of observation, and that no influence can propagate faster than the speed of light. The quantum mechanical description of entangled particles seemed to violate at least one of these principles, suggesting to Einstein that there must be some deeper theory underlying quantum mechanics that would restore locality and realism. The EPR argument was elegant and deceptively simple in its logic. Consider two particles that interact and then separate, flying apart to distant locations where Alice and Bob perform measurements on them. Quantum mechanics predicts that if Alice measures a certain property of her particle, she can instantly predict with certainty the outcome of Bob's measurement of the corresponding property on his particle, even though they're separated by vast distances. Einstein argued this meant the particles must have carried definite values for these properties all along, predetermined by hidden variables established during their initial interaction. Otherwise, Alice's measurement would have to instantly influence Bob's particle across space, violating the principle of locality that Einstein held sacred. For decades, the EPR paradox remained a philosophical debate rather than an experimentally testable question, with physicists divided between those who accepted quantum mechanics as complete, despite its apparent non-locality, and those who believed hidden variable theories would eventually restore classical intuitions about reality. Then, in 1964, John Stuart Bell, a physicist working at CERN, discovered something remarkable that transformed the EPR debate from philosophy into experimental science. Bell proved mathematically that any theory based on local hidden variables, any attempt to explain quantum correlations through predetermined properties while maintaining locality, must satisfy certain inequalities that constrain the strength of correlations between measurement outcomes. These Bell inequalities represent limits on how strongly correlated two distant measurements can be if the particles carry predetermined values for the measured properties and if no faster than light influences exist between them. Bell's stroke of genius was recognizing that quantum mechanics actually predicts violations of these inequalities, correlations stronger than any local hidden variable theory could produce, providing a way to experimentally test whether nature follows the predictions of quantum mechanics or whether Einstein's hidden variable intuitions might be correct. The Bell inequalities can be understood through a thought experiment involving measurements of particle spins or photon polarizations at different angles. In local hidden variable theories, particles carry definite, though unknown, values that determine how they'll respond to measurements at various angles, and the correlations between Alice and Bob's measurements depend on comparing these predetermined responses. Bell showed that such theories must satisfy mathematical constraints on the statistical correlations, bounds that quantum mechanics violates by predicting stronger correlations that seem to require non-local connections between distant measurements. The simplest version, the CHSH inequality named after Clauser, Horn, Shimony, and Holt, involves measurements at 4 different angle settings and predicts that a certain combination of correlation coefficients cannot exceed the value of 2 if local realism holds. Quantum mechanics predicts this combination can reach approximately 2.82, a dramatic violation that experiments have confirmed thousands of times over the past 5 decades. The experimental tests of Bell's inequalities began in the 1970 seconds and 1980 seconds, with pioneering work by John Clauser, Alain Aspect, and their collaborators, using entangled photons produced through atomic cascades and nonlinear optical processes. Aspect's experiments in the early 1980 seconds were particularly ingenious, using rapidly switching analyzers to close potential loopholes that might allow local hidden variable explanations through communication between detectors. These groundbreaking experiments consistently showed violations of Bell's inequalities in agreement with quantum mechanical predictions, demonstrating that nature really does exhibit the spooky correlations that troubled Einstein so deeply. The measurements revealed correlation strengths around 2.7, well above the local realism bound of 2 and close to the quantum mechanical prediction of 2.82, providing compelling evidence that either locality or realism, or both, must be abandoned to account for the observed phenomena. But critics pointed out potential loopholes that might allow local hidden variable theories to survive by exploiting experimental imperfections. The detection loophole arose because early experiments detected only a small fraction of produced photon pairs, potentially allowing local hidden variables to exploit this inefficiency by predetermining which particles would be detected. The locality loophole existed because the detector settings weren't changed fast enough, or the detectors weren't separated far enough to ensure that no light-speed signal could coordinate the measurement outcomes. For decades, various experiments closed different loopholes individually, but none closed all loopholes simultaneously in a single experiment that would definitively rule out all possible local hidden variable theories. That changed in 2015 when multiple research groups performed loophole-free Bell tests that simultaneously closed the detection and locality loopholes with overwhelming statistical significance. The experiment by the Delft group, led by Ronald Hansen, used entangled electron spins in nitrogen vacancy centers in diamonds separated by more than a kilometer, with detection efficiencies high enough to close the detection loophole and rapid random setting choices, ensuring no lightspeed signal could coordinate the measurements. Other experiments by groups in Vienna and Boulder used entangled photons with high detection efficiency and carefully designed protocols to close all known loopholes, providing definitive confirmation that Bell's inequalities are violated in nature. The statistical significance of these loophole-free experiments was extraordinary, with some showing violations with confidence levels exceeding 11 standard deviations, making it essentially impossible to explain the results through local hidden variables or experimental artifacts. These experiments earned Alain Aspect, John Clauser, and Anton Zeilinger the 2022 Nobel Prize in Physics for their pioneering work, establishing the reality of quantum entanglement and ruling out local hidden variable theories. The loophole-free Bell tests represent one of the most profound experimental results in the history of science, forcing us to abandon either locality or realism in our description of nature and confronting us with the unsettling conclusion that reality at the quantum level behaves in ways that fundamentally contradict our classical intuitions about causality and the independence of distant events. But here's where the paradox deepens in ways that challenge our understanding of information, causality, and the structure of spacetime itself. If measuring one particle instantly affects the state of a distant entangled partner, violating locality in apparent contradiction with special relativity's prohibition on faster-than-light causation, why can't we use entanglement to send information instantaneously across vast distances? This question leads to what physicists call the no-signaling theorem, a fundamental result showing that despite the non-local correlations in entanglement, Alice cannot use her measurements to transmit information to Bob faster than light because the outcomes of Bob's individual measurements appear completely random until he compares his results with Alice's measurements through classical communication channels. The randomness of quantum measurement outcomes prevents entanglement from being weaponized for superluminal communication, preserving the causal structure of spacetime, even while allowing non-local correlations that seem to violate locality. This creates a peculiar situation where nature exhibits non-local correlations that Einstein would have considered impossible, yet simultaneously prohibits using these correlations to violate causality by sending messages backward in time or faster than light, maintaining a delicate balance that preserves relativistic causality while allowing quantum non-locality. The tension between quantum non-locality and relativistic locality has led physicists to carefully distinguish between different notions of locality, recognizing that Bell's theorem rules out local hidden variables but doesn't necessarily violate the spirit of relativity if we interpret entanglement as revealing pre-existing correlations in the quantum state rather than instantaneous causal influences. The measurement problem in quantum mechanics adds another layer of mystery to the story of quantum reality and its apparent violation of classical intuitions. According to the standard Copenhagen interpretation developed by Niels Bohr and Werner Heisenberg in the 1920 seconds, quantum systems exist in superpositions of multiple states simultaneously until a measurement collapses the wave function to a definite outcome, but this collapse process seems to contradict the deterministic evolution described by the Schrödinger equation that governs quantum systems when they're not being measured. Before measurement, a particle can exist in a superposition of being in multiple locations, having multiple velocities, or possessing multiple values for any quantum property, with the wave function describing the probability amplitudes for finding each possible value upon measurement. The act of measurement somehow forces this fuzzy superposition to collapse into a single definite outcome, but the Copenhagen interpretation provides no mechanism for this collapse and offers no clear definition of what constitutes a measurement or where the boundary lies between the quantum and classical worlds. This measurement problem has troubled physicists and philosophers for nearly a century, leading to numerous competing interpretations of quantum mechanics that attempt to resolve the apparent contradiction between superposition and collapse, between the deterministic evolution of the wave function and the random outcomes of measurements. The many-worlds interpretation, proposed by Hugh Everett in 1957, offers a radical solution to the measurement problem by denying that wave function collapse ever occurs at all. Instead, Everett suggested that all possible measurement outcomes actually happen in different branches of a vast multiversal tree, with the universe splitting into multiple copies every time a quantum measurement occurs, creating separate realities for each possible outcome. In this view, when Alice measures the spin of her entangled particle and finds it pointing up, the universe branches into two copies, one where Alice observes spin up and Bob's particle has spin down, and another where Alice observes spin down and Bob's particle has spin up, with each version of Alice and Bob experiencing their branch as the only reality. The many-worlds interpretation eliminates the need for wave function collapse and treats all of quantum mechanics as purely deterministic, but at the cost of accepting that an unimaginably vast number of parallel universes exist where every possible quantum outcome is realized. Critics argue that many worlds faces serious problems in explaining why we experience definite measurement outcomes if all possibilities are equally real, and the interpretation struggles to derive the Born rule that predicts the probabilities of different outcomes from the structure of the wave function alone. Supporters counter that many worlds is the most parsimonious interpretation because it takes quantum mechanics completely seriously without adding extra postulates about collapse, treating the wave function as a complete description of reality and measurement as simply the entanglement of measuring apparatus with measured system, creating correlations between branches without any actual splitting or multiplication of universes. The de Broglie-Bohm pilot wave interpretation takes the opposite approach, restoring complete determinism and realism by proposing that particles always have definite positions guided by a quantum potential derived from the wave function. In this hidden variable theory developed by Louis de Broglie in the 1920 seconds and rediscovered and refined by David Bohm in 1952, particles follow deterministic trajectories through space, but their motion is influenced by a non-local pilot wave that depends on the configuration of all particles in the universe, naturally explaining quantum non-locality and entanglement through explicit faster-than-light influences in the guiding equation. The pilot wave theory reproduces all the predictions of standard quantum mechanics for measurement outcomes, while providing a clear ontology where particles always have definite properties and the randomness of quantum mechanics reflects our ignorance of initial conditions rather than fundamental indeterminism. However, the theory's explicit non-locality and its privileged notion of simultaneity seem difficult to reconcile with special relativity, and many physicists find the theory unnecessarily baroque compared to the elegant mathematics of standard quantum mechanics. The theory also struggles to extend to quantum field theory and particle creation and annihilation processes, though researchers continue to develop relativistic versions that attempt to preserve the theory's virtues while addressing these challenges. Spontaneous collapse theories represent yet another approach, modifying the Schrödinger equation to include random collapses that occur spontaneously without any measurement, solving the measurement problem by making collapse a physical process built into the fundamental laws rather than an additional postulate. The GRW theory, named after Girardi, Rimini, and Weber, proposes that each particle undergoes spontaneous random collapse at a very low rate, perhaps once every 100 million years, but with collapse rates amplifying dramatically for macroscopic objects containing enormous numbers of particles, ensuring that quantum superpositions rapidly collapse into definite states as systems grow larger. This elegant idea explains why microscopic quantum systems can maintain superpositions for long times, while macroscopic objects always appear in definite states, providing a natural boundary between quantum and classical behavior without invoking consciousness or observation. The theory makes predictions that differ slightly from standard quantum mechanics in principle, though experiments haven't yet reached the sensitivity needed to test these differences, and future experiments using increasingly large quantum superpositions might be able to detect the spontaneous collapse process if it exists. Critics point out that spontaneous collapse theories introduce new parameters whose values must be carefully tuned to match observations, and the energy non-conservation implied by collapse processes raises theoretical concerns, though some physicists view these as acceptable costs for solving the measurement problem. Quantum Bayesianism, or cubism, offers a radically different perspective, interpreting quantum states not as objective properties of physical systems, but as representations of an agent's subjective beliefs and expectations about future measurement outcomes. In this view, championed by Carlton Caves, Christopher Fuchs, and Ruediger Schack, the wave function describes an observer's state of knowledge rather than an element of physical reality, and wave function collapse simply represents updating one's beliefs upon gaining new information through measurement. Cubism dissolves the measurement problem by denying that there's any objective quantum state that needs to collapse, treating quantum mechanics as a set of rules for agents to organize their experiences and make predictions rather than a description of observer-independent reality. This radical subjectivism troubles many physicists who believe science should describe objective reality independent of observers, but cubists argue their interpretation resolves numerous quantum paradoxes by recognizing that different observers can assign different quantum states to the same system based on their different information without any contradiction, since quantum states are fundamentally personal rather than universal. The interpretation raises deep questions about whether objective reality exists at all, or whether the universe is fundamentally about experiences and observations, rather than underlying physical substrates, connecting quantum mechanics to age-old philosophical debates about idealism and realism. The relationship between quantum mechanics and consciousness represents one of the most controversial and speculative areas in foundations of physics, with some physicists and philosophers arguing that consciousness plays a fundamental role in collapsing wave functions, while others dismiss such ideas as unscientific mysticism. The idea that consciousness causes collapse dates back to early quantum pioneers, including John von Neumann, who argued mathematically that the chain of quantum entanglement during measurement must terminate somewhere, suggesting that conscious observation provides the necessary cut between quantum and classical description. Eugene Wigner extended this reasoning in his friend thought experiment, imagining a conscious observer measuring a quantum system inside a sealed laboratory, while Wigner describes the entire laboratory, including his friend, as a quantum system in superposition, creating an apparent paradox that Wigner resolved by suggesting consciousness collapses the wave function, allowing his friend's conscious observation to create a definite outcome. Modern versions of Wigner's friend thought experiments, particularly extensions involving multiple friends and observers, have generated renewed interest by showing that different observers can assign conflicting quantum states to the same systems, potentially creating logical contradictions that might be resolved by appealing to consciousness or by abandoning observer-independent facts about measurement outcomes. However, most physicists remain skeptical about consciousness-based interpretations, arguing that they anthropomorphize quantum mechanics unnecessarily, and that decoherence through environmental interaction provides a sufficient explanation for the emergence of classical behavior without invoking subjective experience. Quantum decoherence has emerged as the most widely accepted framework for understanding how classical behavior emerges from quantum mechanics without requiring consciousness or mysterious collapse postulates. Decoherence theory, developed by Heinz-Dieter Zeh, Wojciech Zurek, and others in the 1970 seconds and 1980 seconds, recognizes that real quantum systems are never truly isolated, but constantly interact with their environments through photons, air molecules, thermal radiation, and other ubiquitous influences. These environmental interactions entangle the system's quantum state with enormous numbers of environmental degrees of freedom, rapidly spreading quantum coherence across such vast Hilbert spaces that interference effects become practically impossible to observe, creating the appearance of wave function collapse even though the full system remains in a pure quantum superposition. The decoherence timescale for macroscopic objects is extraordinarily short, often just femtoseconds or less for everyday objects interacting with room temperature environments, explaining why we never observe superpositions of chairs or cats in everyday life. Decoherence successfully explains many features of the quantum to classical transition, including why certain properties like position decohere much faster than others, and why measurement outcomes appear in preferred basis states rather than arbitrary superpositions. However, decoherence alone doesn't fully solve the measurement problem because it only explains the disappearance of observable interference effects, not why we experience definite outcomes rather than remaining in superpositions of having observed different results. The combination of decoherence with various interpretations like many worlds, quantum Bayesianism, or spontaneous collapse provides different complete resolutions to the measurement problem, with ongoing debates about which approach best captures the nature of quantum reality. The experimental frontiers of quantum entanglement and superposition continue to push the boundaries of what's possible, with researchers creating increasingly large and complex quantum states that challenge our intuitions about where quantum mechanics stops and classical physics begins. Quantum computers represent the most dramatic application of controlled quantum superposition and entanglement, using qubits that exist in superpositions of 0 and 1 to perform calculations that would be impossible for classical computers. Google's quantum supremacy experiment in 2019 demonstrated that a 53-qubit quantum processor could perform a specific calculation in 200 seconds that would take classical supercomputers thousands of years, though the practical significance of this particular calculation remains debated. IBM, IonQ, and other companies are racing to build larger and more stable quantum computers with hundreds or thousands of qubits, targeting applications in drug discovery, materials science, cryptography, and optimization problems, where quantum algorithms could provide exponential speedups over classical approaches. The main challenge facing quantum computers is decoherence, as environmental interactions cause qubits to lose their quantum properties within microseconds or milliseconds, limiting the complexity of calculations that can be performed before errors accumulate. Quantum error correction codes can, in principle, overcome decoherence by encoding logical qubits in entangled states of many physical qubits, allowing errors to be detected and corrected. But implementing these codes requires thousands of physical qubits to create a single, reliable logical qubit, a threshold that current technology is approaching but hasn't yet crossed. Quantum communication and quantum cryptography exploit entanglement to create communication channels with security guaranteed by the laws of physics rather than computational complexity. Quantum key distribution protocols like BB84, invented by Charles Bennett and Gilles Brassard in 1984, allow two parties to establish a shared secret key by encoding information in quantum states of photons, with any eavesdropping attempt necessarily disturbing the quantum states in detectable ways due to the no-cloning theorem that prohibits copying unknown quantum states. China's Messier satellite, launched in 2016, demonstrated quantum key distribution over distances exceeding 1,200 kilometers between ground stations, proving the feasibility of satellite-based global quantum communication networks. European and American initiatives are developing similar quantum communication infrastructures, with the ultimate goal of a quantum internet, connecting quantum computers and sensors in networks, where entanglement distribution enables capabilities impossible with classical communication. Quantum teleportation, first demonstrated experimentally in 1997, allows quantum states to be transferred between distant locations using entanglement and classical communication without the quantum information itself traveling through the intervening space, providing a key building block for quantum networks, though the name is somewhat misleading since no faster-than-light transfer of information occurs. Tests of quantum mechanics in increasingly extreme regimes continue to probe whether the theory breaks down under conditions far from everyday experience. Experiments creating superpositions of larger and larger objects have demonstrated quantum interference with molecules containing hundreds of atoms, with ongoing efforts to reach masses approaching the microgram scale, where gravitational effects might become relevant. These tests aim to determine whether quantum mechanics applies without modification to arbitrarily large masses, or whether some new physics emerges at large scales, potentially related to quantum gravity or spontaneous collapse mechanisms. The proposed LIGO-like experiments to detect quantum signatures in gravitational waves from merging black holes represent ultimate tests of quantum mechanics in strong gravitational fields, potentially revealing where quantum theory and general relativity must be modified to create a consistent quantum theory of gravity. Tabletop tests of quantum mechanics near absolute zero temperature and, in ultra-high vacuum approach, the fundamental limits where decoherence from environments becomes negligible, allowing tests of quantum superposition and entanglement with unprecedented purity and control. These experiments are searching for any deviations from quantum mechanical predictions that might hint at new physics, from spontaneous collapse mechanisms to modifications inspired by quantum gravity theories. The connection between quantum mechanics and the nature of time remains one of the deepest puzzles in physics, with quantum theory treating time fundamentally differently from space in ways that seem difficult to reconcile with general relativity's space-time unification. In quantum mechanics, time appears as an external parameter rather than an observable with its own uncertainty relations, leading to long-standing debates about whether quantum measurements can be performed instantaneously or whether collapse is a physical process that takes finite time. The problem of time in quantum gravity, where both space and time should be treated quantum mechanically, has led to Wheeler-DeWitt equation in which the universe exists in a superposition of different spatial configurations, but the equation contains no time parameter at all, suggesting time might be an emergent rather than fundamental feature of reality. Page and Wouters propose that time itself might arise from quantum entanglement, with one subsystem serving as a clock that creates the appearance of temporal evolution for other subsystems through correlations established by entanglement, providing a potential resolution to the problem of time in quantum cosmology. Recent experiments by Eckert and others have tested temporal aspects of quantum mechanics through quantum clocks and quantum time dilation effects, confirming that time dilation predicted by relativity appears even for quantum clocks in superpositions of different gravitational potentials, unifying quantum and relativistic effects in previously unexplored regimes. The black hole information paradox represents a different kind of quantum puzzle, arising from the apparent conflict between quantum mechanics' reversibility and the irreversible disappearance of information into black holes. When Stephen Hawking discovered in 1974 that black holes emit thermal radiation and eventually evaporate completely, he argued this implied that quantum information could be permanently destroyed, violating the unitarity of quantum mechanics that requires pure states to evolve into pure states, rather than mixed thermal states. The paradox intensified with the discovery that the Hawking radiation emerging from a black hole appears to be exactly thermal, carrying no information about the quantum state of matter that fell in, seemingly erasing information from the universe in violation of quantum mechanics. Attempts to resolve this paradox have led to revolutionary ideas about quantum gravity, including black hole complementarity, which suggests that observers falling into black holes and distant observers might assign different quantum states to the same physical situation without contradiction, challenging the notion of observer-independent reality in quantum mechanics. The holographic principle emerged from studies of black hole entropy, with Gerard Hooft and Leonard Susskind proposing that all information in a volume of space can be encoded on its boundary surface, fundamentally revising our understanding of how information is distributed in quantum gravity. The ADS CFT correspondence, discovered by Juan Maldacena in 1997, provides a concrete mathematical realization of holography, relating quantum gravity in certain spacetimes to quantum field theories living on their boundaries, allowing information paradoxes to be studied through explicit calculations that confirm information is preserved in black hole evaporation when quantum gravity effects are properly included. The firewall paradox, discovered by Almheri, Marolf, Polchinski and Sully in 2012, sharpened the black hole information problem by arguing that preserving quantum information might require a highly energetic firewall at the black hole horizon that would destroy any infalling observer, contradicting general relativity's prediction that nothing special occurs at the horizon of large black holes. The paradox arises from analyzing the entanglement structure of Hawking radiation and the black hole interior, showing that naive attempts to preserve both quantum information and the smoothness of the horizon lead to contradictions that seem to require abandoning either quantum mechanics, general relativity, or the equivalence principle. Proposed resolutions range from ER equals EPR connections between entanglement and wormholes, to suggestions that the interior of black holes doesn't exist as an independent region once enough radiation has been emitted, to ideas about quantum error correction in the structure of spacetime itself. These debates have revealed deep connections between quantum information theory and the structure of spacetime, with some physicists now viewing geometry and gravity as emergent phenomena arising from more fundamental quantum information patterns rather than as basic ingredients of physical law. The cosmological implications of quantum mechanics extend to the origin and evolution of the entire universe, with quantum fluctuations during cosmic inflation potentially seeding all cosmic structure we observe today. The theory of inflation, developed by Alan Guth, André Linde, and others in the early 1980 seconds, proposes that the universe underwent a brief period of exponential expansion in its first fraction of a second, stretching microscopic quantum fluctuations to cosmic scales, where they became the seeds for galaxies and large-scale structure. These primordial quantum fluctuations have been precisely measured through observations of the cosmic microwave background by satellites like Planck, confirming that the pattern of temperature variations matches theoretical predictions for quantum fluctuations stretched by inflation. This represents perhaps the most dramatic observational confirmation of quantum mechanics, showing that quantum uncertainty in the microscopic early universe determined the positions of galaxies billions of light-years across today's cosmos. The measurement problem takes on cosmic significance in this context, raising questions about what caused the collapse of these primordial quantum fluctuations into classical density variations, with some physicists arguing that decoherence through gravitational interactions provided a natural collapse mechanism, while others suggest the many worlds interpretation applies with each quantum branch, corresponding to a different cosmic history. Quantum mechanics might also determine the ultimate fate and origin of the universe through connections to quantum cosmology and the problem of initial conditions. The Wheeler-DeWitt equation attempts to describe the quantum state of the entire universe, treating spacetime geometry itself as a quantum observable in superposition, but the equation's interpretation remains deeply mysterious and controversial. The Hartle-Hawking no-boundary proposal suggests the universe's initial state can be computed as a path integral over compact geometries with no boundary, potentially explaining why our universe has the properties it does without requiring special initial conditions to be imposed by hand. Alternative approaches like Penrose's conformal cyclic cosmology propose that quantum mechanics allows the universe to undergo infinite cycles of expansion and rebirth, with each cycle beginning in a hot, dense state, but stretching to infinite size and zero temperature before quantum processes trigger a new Big Bang. These speculative ideas connect quantum mechanics to the deepest questions about why the universe exists, why it has the properties it does, and whether existence itself requires quantum mechanical principles that transcend space and time. The philosophical implications of quantum mechanics continue to generate heated debates about the nature of reality, causation, and scientific explanation nearly a century after the theory's development. Einstein's famous question about whether the moon is there when nobody looks captures the core challenge quantum mechanics poses to naive realism, the common-sense view that objects have definite properties independent of observation. The Copenhagen interpretation suggests measurement creates reality rather than merely revealing pre-existing properties, leading to Bohr's complementarity principle that quantum systems cannot be understood in terms of classical concepts, but only through the complementary aspects revealed in different experimental contexts. This instrumentalist view frustrated Einstein and other physicists who believed science should describe objective reality rather than merely predicting measurement outcomes, leading to his insistence that God does not play dice and his conviction that quantum mechanics must be incomplete. The debates between Bohr and Einstein at the Solvay conferences in the late 1920 seconds and early 1930 seconds remain among the most profound philosophical exchanges in physics, with each defending radically different visions of what physical theories should accomplish and what kinds of reality they should describe. Contemporary philosophers of physics continue debating whether quantum mechanics should be interpreted realistically as describing mind-independent reality or instrumentally as merely a tool for organizing experiences and making predictions. Structural realists argue that quantum mechanics reveals the relational structure of reality rather than the intrinsic properties of things, with entities defined by their relations and correlations, rather than possessing independent existence. Ontic structural realism goes further, suggesting that only structure is real and that individual objects are derivative abstractions from underlying patterns of relations and symmetries. These philosophical positions connect to debates about scientific realism more broadly, including arguments that the history of science shows theories we once believed were true were actually false, suggesting we should adopt an agnostic stance toward current theories like quantum mechanics rather than taking them as literal descriptions of reality. Defenders of scientific realism counter that quantum mechanics' unprecedented empirical success and the way it unifies previously disconnected phenomena provides strong evidence for its approximate truth, even if we don't yet fully understand what kind of reality it describes. The role of mathematics in quantum mechanics raises additional philosophical puzzles about the relationship between abstract mathematical structures and physical reality. Eugene Wigner famously wrote about the unreasonable effectiveness of mathematics in physics, marveling at how abstract mathematical constructs like complex Hilbert spaces and operator algebras precisely describe physical systems without any obvious reason. Why mathematics should apply to the physical world? The complex number-valued wave function seems particularly mysterious, with the imaginary unit appearing fundamentally in the Schrödinger equation, despite never being directly observable in measurement outcomes. Some physicists and philosophers embrace mathematical Platonism, arguing that mathematical structures exist independently in a realm of abstract forms and physical reality somehow instantiates or participates in these mathematical truths. Others adopt nominalist positions, viewing mathematics as human constructions useful for modeling, but not literally existing beyond our symbolic manipulations and cognitive practices. The debate connects to questions about whether physics discovers or invents its mathematical descriptions, whether mathematics describes physical reality or merely provides tools for calculation, and why one particular mathematical structure, the quantum mechanical Hilbert space formalism, seems to capture nature's behavior at small scales. The future of quantum foundations research promises deeper insights into the nature of reality as experimental and theoretical tools become more sophisticated. Quantum computers will eventually test quantum mechanics in regimes of unprecedented complexity, creating entangled states of thousands or millions of qubits that exist nowhere else in nature, and challenging our understanding of how classical behavior emerges from quantum substrates. These tests might reveal breakdowns of quantum mechanics at large scales, or confirm that quantum principles apply without modification to macroscopic systems, settling long-standing debates about collapse mechanisms and the measurement problem. Space-based quantum experiments aboard satellites and space stations will test quantum mechanics in microgravity and against cosmic ray backgrounds, searching for environmental decoherence sources that are absent in terrestrial laboratories and testing proposed modifications to quantum theory inspired by quantum gravity. The combination of increasingly sophisticated experiments with new theoretical approaches, drawing on quantum information theory, quantum field theory in curved spacetime, and string theory insights, promises to deepen our understanding of how quantum mechanics relates to spacetime, gravity, and the structure of reality itself. The implications of quantum mechanics extend beyond physics to influence our understanding of life, consciousness, and the possibility of quantum effects in biology. Quantum coherence effects have been discovered in photosynthesis, where plants exploit quantum superposition to search multiple energy transfer pathways simultaneously, achieving near-perfect efficiency in converting light energy to chemical energy. Bird navigation and olfaction might involve quantum entanglement and superposition, with magnetoreception possibly relying on radical pair mechanisms where entangled electron spins respond to magnetic fields through quantum interference effects. These quantum biology phenomena demonstrate that evolution has found ways to exploit quantum mechanics for functional advantages, despite the challenge of maintaining coherence in warm, wet environments that typically cause rapid decoherence. The possibility of quantum effects in brain function and consciousness remains highly controversial and speculative, with Roger Penrose and Stuart Hameroff proposing that quantum superpositions in neuronal microtubules might play roles in conscious experience through orchestrated objective reduction processes. Most neuroscientists remain skeptical, arguing that brain temperatures and environments would cause decoherence far too quickly for quantum effects to influence cognition, but the question remains open and fascinating, given our deep ignorance about the physical basis of consciousness. The technological applications of quantum mechanics are revolutionizing multiple fields beyond computing and communication, with quantum sensors achieving sensitivities that approach fundamental limits imposed by quantum uncertainty. Atomic clocks based on quantum superpositions now reach precisions better than 1 second in 30 billion years, enabling tests of relativity, searches for dark matter through variations in fundamental constants, and unprecedented accuracy for GPS and navigation systems. Quantum magnetometers can detect magnetic fields billions of times weaker than Earth's field, with applications ranging from mineral prospecting to medical imaging of brain activity. Gravitational wave detectors like LIGO operate at the quantum limit, where measurement precision is constrained by uncertainty, relations between position and momentum, requiring quantum squeezing techniques that manipulate quantum states to reduce noise in one observable at the expense of increased uncertainty in complementary observables. Future quantum sensors might detect dark matter directly through quantum decoherence effects, measure gravitational fields with enough precision to test modifications to Newtonian gravity on laboratory scales, or image biological processes at the cellular level by detecting magnetic fields from ion channels and nerve signals.